being in control and staying agile with graph requires shifting left. I'll break that title down in a few minutes, but before that I want to give a bit of inspiration. This is my Lego set. It's called the architecture kit, and it only includes white blocks and see-through blocks. And the whole thing about the set is it's designed to help you abstract buildings away. So you get to build up a building, and then you break it down, and then you can find another inspiration, and you can build it up. To bring a little bit of the Dutch inspiration, there's this beautiful building in Amsterdam. It's called the Amsterdam Eye, and it's actually a film museum. And I tried to make this building using the architecture kit, and it took me about 2 days breaking it up, building it. Oh, it was terrible. But I'm quite proud of my results. It came out like this, and you got all the angles in. So this Lego kit actually gave us a lot of inspiration for the architecture that we're going to be talking about. Going back to the title, being in control is all about security, scalability, data quality. And we in the financial industry think we are unique in this. But actually, I think everyone is needing to be in control. If you look at all the news lately, with all the loss of data and all the events that are happening, I think most of us need to be really aware of what it means to be in control. Staying agile, on the other hand, means that we get new insights. Time to market is really important. We get new features. We need to build these things quickly. That means our design needs to take this into consideration. We also have to have a pluggable architecture. And one way to manage this very well is to make a pipeline. And going into shifting left, it's not a new concept. It's a very old concept. But shifting left effectively means taking as much of your operational work and moving it to the design and the build phase. So that way you do less on the operation side. So you have to start designing for no migrations. One of the things that we also realized is systems are best designed to not last long. This will actually help you be more agile and more in control. A short introduction. My name is Gary Stewart, and this is Will. I'm a datastore platform architect, and I'm primarily responsible for the NoSQL databases within ING.
Hi, so my name is Will Bleker. I'm the chapter lead for the events and datastore team within ING. And we take care of platforms for Apache Kafka and Apache Cassandra type data stores. Unlike Gary with his Lego, I'm more of an old school guy liking big steel metal works, so not so much the building and the breaking. I more enjoy the long-term things, hence I've got the train and he's got the car. So we'll see these come back into our slides and see why it's relevant. Both of these still have a place in our society nowadays. So for those unfamiliar with ING, we're a global financial institution based mainly in the Netherlands. But we operate in over 40 countries worldwide and have about 52,000 employees. So everything we do, everything we design and build, we need to keep that in mind. Because we might build it in Europe, but it has to work in Asia or in America or any part of the world. So things that we build need to be easily adjustable and agile. We need to be able to plug them in anywhere in the world. So with that in mind, let's start with the talk. We're going to break this up into 4 sections. We're going to start with a bit of the concepts of how we do, how we think. Then the pipelines we use to actually make this work. And then go into one of the use cases that we've actually used Neo4j in. And then as a final bit, we'll show some of the learnings, graph learnings that we've came up with in the last couple of months. So before I go any further, I guess most of you are aware or know about the analogy of pets versus cattle. So a guy back in 2011, 2012, Bill Baker, He was struggling to explain the difference between scaling up and scaling out. And he basically came up with the analogy that you've got pets and you've got cattle. Pets are your unique servers. They're mostly one-off. When you need more throughput from them, you generally scale up. And these things also tend to have a rather long lifespan. And moving to the cloud, we're moving towards more cattle-like architecture, so things that are disposable. They're one of a herd. Quite often these things are also pipelined, so it's simple redeploy when something goes wrong. And you scale them out, and you also see there that they're mostly based on an active-active type of architecture. And the databases, the data stores that we support in our team, Apache, Kafka, and Cassandra, they fall mostly under this cattle type of architecture. So because I screw it up, I keep on saying pets versus cats and all kinds of other iterations, we decided to come up with trains versus cars. Plus it would look good on a shirt, so. When we look at our data stores, they're just like the transport industry. In the last couple of years, they've gone through a couple of transformations. And there's still a place for all of them, but in general, if we look at trains, it's a once-off thing. It's a long-lived item, and it's built on demand. Whereas cars, on the other hand, by now, it's gone from manual to a fully automated process. It's become mass-produced, and it's almost become a consumable product. So when something happens to your car, if you have a bad accident or it's just old, you simply replace it for a new one, unlike a train that has a bit longer lifespan. Also, when you look at the way that we use these, trains, you pack them full of people, they all leave at the same time, they follow a fixed schedule, and they arrive all at the same time. If something should happen in this train halfway through our journey, then all the people in the train are delayed. And same as in our database landscape, we've noticed, or in our IT landscape for that matter, we've started noticing more and more that, sometimes it's okay for certain parts to not arrive at the same time. So we need that bit of flexibility, and hence we scale out towards cars, because you have smaller amounts of people in a car, and should one have a problem, well, only part of your data will be delayed. So our journey started from a relational database onto NoSQL, and this was quite a big mindset change. We chose Cassandra purely for the high availability and the scalability options that you get with Cassandra. But it also brought along things like tunable consistency and replicas and a whole bunch of other things that seemed quite daunting at the beginning. But after using it for roughly 4 years now, we've grown so accustomed to how these databases work and the added benefits you get from them. For example, lifecycle management has now become a breeze. We've actually got a lot more weekends free, because in a typical master-slave, active-passive type of environment, you end up having to schedule downtime, you need to switch between your databases. And in an active-active solution like Cassandra, we simply do our patches during the daytime. Office hours really doesn't matter. So we've kind of gotten some liquid expectations of any new technology that we want to adopt in the future. It also has to follow these kind of rules and these features that we have. We don't want to go back to working weekends. So about a year ago, we noticed there's a real big gap in our landscape that can easily be filled by a graph database to get to grips of our connected data. And we didn't want to go down the route of another active-passive or leader-follower type solution. So we had to figure out ways to work around these challenges and keep our weekends free. So other interesting observations, if you look at other databases, for example, the key value store, it's quite easy to mess up a partition, but it's only the partition then. And in a relational database, well, you mess up a table with a simple query. But in a graph database, it's quite easy to screw up your whole database. So with these and our weekends in mind, we had to think about ways to work around this problem. So Gary's going to tell us a bit more of how we achieve that.
Yes. So actually, when you take any architecture, you always have a system of records, and generally the path is that the demand increases or the types of queries increase, and then you start having performance problems. I think we can all relate to that. Then what we decide is we're going to put a cache in between. Now that cache can be any database to solve the problem. So it could be Neo4j, it could be Cassandra, it could be any other database. So now you've got a cache, but the data doesn't magically get there, so then you have to build a batch loader or an export. This can be off-the-shelf tools, doesn't really matter. However you do it, you'll have to manage that. And then, of course, you need to build your APIs to use this cache database, and generally speaking, you don't want to write in your cache. You normally just read from your cache, and then you would write in your system of records. And then finally, you realize, but hang on, now I only have data at a moment in time, so I need to add a real-time sync. So then we put the real-time sync in. So this is a lot of work, etc. And of course, you start realizing that I need a resilience pattern between each component. So the APIs have to be resilient on the cache databases, and then the cache databases and the batch loader have to be resilient, the real-time sync has to be resilient, and then it just gets more ugly when you want to be in multiple data centers. So you actually start realizing that lifecycle management is hard. Each thing has versioning, cross-data center resilience, etc., etc. So we decided that we don't really like this very much anymore. And again, this is per use case, so you have to figure out what fits where. But we decided that maybe we need to simplify this. So what if we were to just put all those components into one car, if you will, and then basically manage that on its own, so that you don't have APIs calling different instances of databases. You get comfortable with rebuilding. You actually have all your code there to rebuild fast. You don't have to do migrations. If you want to do availability, you just deploy an instance in each data center. So it gets a lot easier to reason with. And when you're using technology like Neo4j, all the data must fit on one node anyway, so you're actually not more restricted than before. But this is all fine and well. We can actually make this even more simple. When you use technology like Kafka, which has features called compacted topics, you can actually get rid of the batch files and then use the compacted topics to sort of design that away, because managing files is also a security place, and then you have to build in all the mechanisms for that. We're not going to go too much details into Kafka because that's a talk on its own, but just to know that you can design the components even, take some components out by using Kafka. And you can even take it one step further, because we do like cars, and we see Kafka as a car and our cache database as a car. A lot of use cases can actually use Kafka or any other technology like that for a system of records, and then you get comfortable with a materialized view. So when you break a database down into two parts, a commit log and a materialized view, then you basically use one technology for the commit log and another technology for the view of that data. And to build that up, we'll take over for the pipeline.
Yeah, so we're building a whole lot of things here, and we want to build them a lot and quite often. So how do we do that? Well, first of all, let's put a pipeline in, because we don't want to be building things up manually every day. So in this example, we've got two cars running, and the car is then the consumer on the one side, the batch loader, the real-time sync, the API for the customers, and also the Neo4j database. And this can run in a Docker container or a VM or whatever technology you use within your company. And then a load balancer on the right-hand side there that basically distributes the load across these two machines. So let's say we've got a new feature, or one of the cars broke down and we want to put a new one in. We add a new VM or Docker container. We block all the ports to make sure that no client connections can come in and query the database or the application whilst it's being built up. Then the second step is to get all the stuff, and with stuff I mean things like artifacts, the libraries, the binaries, everything that you need to build up a car. Same as in the car industry, they make sure that they've got all the components in the factory to build up a car from A to B. So we get all our stuff on the machine itself, so no network hiccups can cause problems during the build process. Then we start with a pre-processing phase, where we source all our data from the system of records, so Kafka on this side. We convert the data into whichever format we need. In our case, it was a CSV file. And then we use a tool, the Neo4j admin import tool, which I'll cover a bit later, to import the data into our application, into our car. Then we start up the database, and then after that we've got a couple of post-processing steps. And that includes things like creating indexes and running other complex queries to start up our applications and the rest of our car. Once that's all done successfully, we actually unblock the ports and then perform the switch. And then we take out the old one and the new one's running without any downtime for the application. So I touched briefly on the admin import. This is a key tool for when you want to rebuild quite often. You got a bunch of data that you want to get into your database quite often and quite fast. So in this example here, we've got a simple model with a source, which in our case was a host, a server. And then we've got a bunch of messages that come in that relate to this source. So then you'd use the admin import tool. Do note that this can only be used once, and when the database is still empty for those that haven't used this before, because it bypasses the transaction manager, and that also gives it a speed in importing loads of data. So we import two CSV files with nodes, the sources and the messages, and then a third one with all the relationships. And what that looks like is the sources, so the nodes look, you'd have an ID, a name, and a label. And the relationships, you basically need a start ID, end ID, and the type of label that you're importing. So we ran this on our use case, and we managed to import 11 million nodes and 11 million relationships in just over 4 minutes, which seems quite good, especially if you're rebuilding quite frequently. But seeing as we started rebuilding 4 or 5 times per day, and our clusters, our environments that kept on growing and getting more and more data, we needed to optimize this. And a quick little hack to get to these kind of numbers. So basically in a third of the time, we managed to import more than double the amount of nodes and relationships. An easy way to get that is by changing the names of the IDs. An ID is only used during the importation. It's not real data. Just make sure you don't have duplicate names there. But if you work around that problem, you decrease the size of the file and hence also the amount of data coming through the admin import tool. And, well, dramatic increases in your performance. So we had to use this somewhere, and our use case was for managing our Cassandra platform. So not the first place you would think to use a graph technology, but we wanted to stay in control of our clustered environments. Because we started playing with graph with Neo4j about a year ago, and we know that we manage our Cassandra environment that consists of multitude of nodes in multitude of clusters. And on those clusters, we again have loads of customers that all consume key spaces. And we know there's big numbers, and we've got a lot of clients to deal with, and a lot of components, a lot of other departments within our company that we have to deal with. But it's only once you start putting that data into like a graph database, and you can visualize it and start going through, you realize how many components you have to deal with. Now, this is pretty much business as usual, because rapid growth, dependencies, every other company has this. But we wanted to stay in control of our clusters. Because what we were seeing is that as soon as an incident occurs on an environment, and it's a multi-tenant environment, I didn't mention that earlier, but we've got loads of customers on our environment, all with their own needs and their own use cases. So if something happens on one of our clusters, we would see the operators log into a multitude of nodes, running all kinds of queries to find where the problem is, looking at all the different components and trying to, in their own heads, get the links, lay the links between the problems. And we thought there must be a better way for this. We needed to pipeline this because we don't value initial bursts of energy anymore. That's a once-off thing. We need to pipeline our heroes. We need to find a way to work around this problem. And plus, on a side note, we wanted to learn graph a bit better, so we started to use graph for our problem here. So what we did is we have a simple architecture. We have a producer on the one side, a queue in the middle, and a consumer on the other side. The producer is something really simple, really efficient. It's a small little binary that runs on all of our nodes and basically runs the commands that all the operators would do once they would log into the machines to try and get information about them. That information is passed onto the queue and consumed by the consumer, which is a much more complex piece of technology. There we do all the parsing of the rules, all the parsing of the data. And so the producer produces just raw messages. We don't do any filtering on there. We don't do any fancy things on the producer. All the raw events are pushed onto the Kafka topic and consumed by the consumer on the other side that does all the parsing. So we've got our producers there on the left side running on all the nodes. Should we need to add new commands, it's basically a configuration file on the node that contains a list of commands that need to be run and the interval at which we want them to run. These raw messages get put onto a Kafka topic. On the other side, we've got the materialized view, so basically the car part of our architecture that Gary explained earlier. And the consumer reads it, transforms the data into the format that we can use for Neo4j, and imports it into Neo4j. So now when we had an incident, before we have an incident, we still got a configuration for certain aspects of our car that we need to manage somewhere. So we store that in GitLab. And the consumer app consumes both from the Kafka topic and from Git to get the state of what we want our environment to be. So now when we get an incident on our environment, instead of logging into all the nodes and trying to find relationships between all the different components within our environment, the operator can now log into the Neo4j database, either via the web interface or a Python script or whatever method they choose, and run queries and find relationships between different components. So this grew quite fast, and we empowered a lot of people with this, and everybody had their own Cypher queries. And that became a bit unmanageable because now we still had the heroes, the guys with the Cypher queries. So we ended up going for an option using GraphGist. I don't know if you guys used it. You get it for free with the trainings. So copy-paste those commands, and it would run. But it's useless if 5 people keep on running the same commands every day. So we thought, let's rather stick that into the consumer, ask the consumer to run these commands every 10 minutes or so, and output that to a static HTML page. So now when something happens on our environment, you don't need heroes with Cypher queries anymore. You simply need someone who can look at an HTML page. Great, so now we've got all this data. We've got the rule sets. We've got a bunch of configurations, values thresholds that we've set for our environment, all stored in Git. Now, when we process these, we can also start putting alerts on them. So we've gone from a simple producer to the consumer, where everything gets parsed, and even notifications to the endpoints.
And if we sort of narrow down into the consumer, because the consumer is actually where a lot of the logic is, but it's also one that gets rebuilt all the time, we would have to parse the message. Because we're doing nothing on the producer side to parse the message, we leave that to the consumer. So the first step is to parse the message. And generally speaking, you write the parser, and then you might have to change the rules later because of new insights, or you want to take some more data out. That we normally break down to key value pairs, so we can get that into the graph database very quickly, because a message on its own is most of the time meaningless. but a message combined with all the other messages from all the hosts and machines, and combined with other message types, that's when the value starts kicking in. So at this point, you can now, once you've got all your data in the graph database, you can actually start doing observations, calculations, and recommendations, because now you can actually start automating this. So we started doing this repeatedly, and whilst we were doing this, we came up with a few principles that just helped guide us to build this correctly. Main principles are that we definitely need an inventory. You need a system of truth. You need to know what you're looking for. If you have a self-discovery system, then you can't always find out what's going on. You can't really, check the reality, so to say. So you have to have your expectations so you can check what's going on. You also, when the team makes agreements, if you can't make the agreements in code and then have that checked once it's been deployed or rolled out, then it starts becoming very difficult to check. So every agreement that the team made, like configuration has to be like this for this type of cluster, and it has to be like that for this type of cluster, put those agreements in configuration, in code, so that you can actually use that in your graph model. One thing I started learning is, I've been doing databases for years, and one of the things that I don't like about Neo4j, at the very minimum, is it's schemaless. On the one hand, I love it. On the other hand, I hate it. Schemaless tends to not allow you to document the data model. So you then have to have another tool if you're rapidly building stuff fast. So I ended up actually documenting a data model. Now, this is something I've never done in my entire 15 years of working with databases. I might actually do it up front and then add it later. So one of the things that we find missing is you can't add comments, you can't add metadata about the model in the graph very easily, or at least we haven't found out how to do that yet. So maybe you can come and let us know if that's possible. But the key one that we wanted to point out was you need to get into the being rebuilding. So when you rebuild your model repeatedly, the next person that comes into the project will be able to learn that project very quickly, because then you understand how things get to where they are. Because a graph model is very functional. You need to understand graph as a technology, but you also need to understand the data that you're working with. We blurred this picture out, by the way, just so you don't actually read all the details on it. It's not that it's confidential, it's just that it's the functional information of the use case that's not really relevant for this talk. But what actually happened, as Will mentioned earlier, we wanted to learn graph. We weren't really fully convinced that it was the best fit for the use case. It actually turned out to be really good for our use case. Where did this actually come from? So we started with about 4 or 5 commands on the producer, and I think within 2 or 3 months we ended up adding 50. And this happened so quickly because we were like little kids in a toy store where we were getting data out that we were just linking stuff, and then we figured out, oh, we can add this. And then we would keep adding configurations to the producer that the momentum was going so fast. We even, for example, put netstats information, and then we were trying to check which applications were connecting to the cluster and if they were connecting to all the nodes and connecting correctly. So just looking at the behaviors of the operational data, we managed to find misconfigured customers. Then we actually realized that our architecture also helped us with this way of thinking. Because it became easy to rebuild, we actually created a learning environment for learning graph. So you could actually quite often make mistakes. And I'll show you some of the mistakes that we made. And then finally, it took us, I think, since we started, over 300 cars were destroyed and rebuilt so that we could actually learn how to use graph and get all our findings after each iteration. So that moves us into the last section, graph learning from NoSQL thinking. So the first thing is, this is one of the lesser known features. So when you get a message and you parse it, and then you would try to get that in the database, you would have to write set property name equals, and then you would have all these long lists. There's actually something called set equals, and then you can use a map, and if you use a plus equals, you can get all of the properties in one go, and you don't actually have to mention the list that is mentioned in the with. So this is a lesser known feature, and I had quite a bit of code for each message type which I managed to throw all the way to this plus. And the reason why this is also interesting is because now we can change the parser rules without having to change the data going into Neo4j. And essentially, you can break everything to key value, and then you can get it into your database, and then you can write your queries after the fact. If you change the parsing rules, then the raw data changes. Then you need to rebuild. And that's something that we did quite often, so we simply rebuilt and we destroyed the old instance. So moving on to our next learning, as I was mentioning, this is actually when I started documenting data model because, again, it's blurred out, but the thing I want to point out is the blue source is in a different place in my model than the yellow source, and those two are not the same. Because we were building so fast, we would add another label or a node, and then we kept adding, and then accidentally we realized that we used the two same names for two actually different objects. Kind of felt like the right name. And when you do the call db.schema, you get a sort of weird linking mess, and then your whole call db schema is not going to help you. And that's why we started documenting the data model to make sure that we don't make these mistakes again. How can you get out of this? You can do property existence, which can protect you in a lot of cases. But in the Cassandra world, we always say you need to solve your reads with your writes. So fix it on your writes, and then you'll actually have an easier read path. So you get this sort of theme. You can now just fix the code and simply rebuild and destroy the instance that's there. This never gets boring. So as Will mentioned, we had a source, which is actually representing a machine for us, one of the produced machines, and each of them have messages. Now, a very simple model, a source has message. I mean, it's not rocket science, but what we forgot was that we were now suddenly adding 50 produced messages, and we were doing it every hour. So over time, the number of nodes attached to that source would be very large. And we always make jokes, if you're too scared to open the node or expand it with the browser, so when you press plus and your browser starts getting a little bit wobbly, then you might want to think about reducing the density of the nodes. So how would you do that? Instead of having a source has message, in this case, for example, it's a functional change, you can then say a source has last message, has previous message, has previous message, has previous message. Because in this use case, most of the time, we only cared about the last message. We didn't really care about all the other ones. We needed it, but it wasn't the main driver. And this is funny, we learned this at the last year's Graph Connect in London, one of the presentations, and we were sitting there going, ooh, that's what we need, that will solve some of our problems. So we came back and we simply changed the code, and then we rebuilt. And then we were out of the old model, which was very nice because no longer do we have the old model anymore. And finally, we talked about never doing a migration. So we thought we might as well do a migration because there's no point in saying migrations are bad if you haven't actually tried. And I quite often write this query: match, optional match, where, and then merge or create or whatever. And essentially the outcome of that is I've destroyed my database. Purely because of one simple mistake, and I often make this mistake, and my reaction is always like this. The thing is, the match, where, optional match, and then merge. The problem with the where being after the optional match, you get a whole bigger data set, and then effectively you do a lot of stuff that you didn't intend to do with the first query. So every time I write one of these queries on the database, I have to basically go and rebuild and destroy the database.
Right, so to conclude, we started off this talk by saying to stay in control and be agile with Graph, you need to, what did I say? Shift left. I wish I could rebuild that one. So, no, you need to shift left. Now, shift left is not an easy thing to do. It requires quite a bit of upfront work. But once you've nailed the shift left and you've designed for rebuilds, you ensure agility. Because by enabling the rebuild feature, you can simply add new features as often as you want and just rebuild. You create a learning environment for people to not be afraid to make changes, because if their change didn't work, they can simply rebuild to the old version. And ultimately, that ensures you that you can keep control over your environment. Because the more often you rebuild your data, the better your data quality will be. You don't have data migrations to work with, so there's no places to mess up your data. And when you want to scale out, you simply spin up X amount of extra nodes. And that's how we stay in control of our environment. So thank you all for listening. And, right.
Looking at the time, I think we have 2 minutes.
3 minutes.
3 minutes even.
Wow.
Wow. So if anyone has any questions, I believe there's microphones over there. Yes.
So on the first one, how many times did we rebuild it? We actually made a nice graph because everything's in Git. We could do a Git log and see. The project started pretty slow, and then all of a sudden it started taking off. So in the last half year, we've done more than 200 rebuilds.
300.
Yeah, we did 300 in a year, but
right,
in the last half year, it was almost over 200. And then the second one was about the relationships.
Second question was, like, you recommend like multiple nodes or multiple relationships. Like, let me give you an example. I have app, that app makes multiple interactions. So I have like app node and interaction node for that particular. So you recommend to create like interaction different nodes, or like you just create multiple relationships?
More relationships or more nodes?
Yeah.
Unfortunately, you're going to hate my answer. It actually depends on the use case and what you're trying to do. For performance, I found that if you're very dense with one node, there's a lot more going on. But you can solve that a little bit with indexing, so it depends on if you're filtering with indexes on properties and nodes, or if you're doing traversing and then through. So it really depends on the query that you're making and the question that you have. Learning from a NoSQL, it's always good to partition. So it's always good to keep things within a good, sane amount of numbers. Because if you have too many nodes, too many relationships to one node, I think that's where you get the biggest problem, or the biggest performance issues. Yeah.
Any more questions? There's one over there. Oh, so I'm sorry, that cannot hear a single word.
How many database instances have you got running at a given point in time?
Oh, that totally depends on how many people are working. How many database instances do we have running?
of Neo4j?
Right now, we've got, for this use case, we've got two database instances. One gold and one bronze. And we basically use the gold one for our production environment and the bronze one for all our other environments. Like I said, we manage our Cassandra environment with this, so all our development, test, acceptance machines, they all push the information to the bronze one, and then the gold one processes the production machines. And then, well, for now, one Neo4j database has been more than sufficient to run the type of queries we need.
The nice thing is with the switching, you can have one running actively, and then whilst you're rebuilding, which takes 20 minutes, then once it's finished, you sort of activate the new one and then you kill the old one. So nobody has any downtime. So you can even have pretty good availability with just one instance. If we were running this in production, then I would definitely do, say, 2 or 3 per data center to service the load of what we were doing. So if we were doing it for customer-facing services, not for production. If we're doing it for customer-facing services, that would be a different paradigm. But for this use case, it's not customer-facing. That answer your question?
All right. that takes us out of time. So
Yes.
thank you all very much for joining.